Hello, so we are looking at infinite limit. Infinite limit. Consider the function f of x, which equals 3 divided by x minus 2. The graph of the function is given below. As we approach positive 2 from the right, the graph of this function increases unboundedly. And as we approach positive 2 from the left, the graph of this function decreases unboundedly. That tells us that the limit of 3 over x minus 2 as x approaches 2 from the right equals positive infinity. And the limit of 3 divided by x minus 2 as x approaches 2 from the left equals to negative infinity. So therefore, the limit as x approaches 2 of 3 divided by x minus 2 will be does not exist. Why? Because the left-handed limit and the right-handed limit are not equal. So if you recollect, in the earlier part, we looked at a function which had a graph looking like this. We wanted to find the limit as x approaches 0. So clearly, the answer to this is positive infinity. Why is it not does not exist? It's positive infinity because both the left and the right-sided limit are approaching positive infinity. So this tells us that the answer to this particular question, as we approach 0 from the right, it goes to positive infinity. And as we approach 0 from the left, it goes to positive infinity. Therefore, the answer to the limit is positive infinity. If we also have another graph which decreases unboundedly, then if we want to find the limit as x approaches 2 of, let's say, a function g of x, well, this is our graph of g of x, clearly the answer to this is negative infinity. Why? Because our graph decreases unboundedly towards negative infinity. So take note of that. So I'd like to give a summary of how to find limit as x approaches infinity. So there are 3 general principles. So let a function which is in the form of a rational function, let's say h of x divided by g of x, provided g of x is not equal to 0. Then, if the power of h of x is greater than g of x, then the limit as x approaches infinity of h of x divided by g of x, this will be equal to infinity. So this is 1. Now let's imagine 2, that the power of g of x, or the power of h of x, is less than g of x. Then the limit as x approaches infinity of h of x divided by g of x, this will be equal to 0. And the third point, imagine the powers are the same. Then the limit as x approaches infinity of h of x divided by g of x will be the coefficient. Let's say we have AB. Then the answer to that will be the coefficient of the 2 functions. So this summarizes how to find limit as x approaches infinity. Now notice here I used only positive infinity, but these 3 rules applies to negative infinity as well. And the answers will be the same. So let's go ahead and look at some examples. So example number 1, You're looking at the limit as x approaches infinity. 3 minus 7x squared divided by 14x squared plus 1. So to solve this, we look for the end behavior model. What is the end behavior model? Take your numerator and look for the highest power of x. Take only that, together with the sign attached to it. And come to your denominator. And take the highest power of x with the sign attached to it. Then simplify this expression. And if you simplify this, we end up with -1/2. So clearly, this tells us that the answer to this equals -1/2. So we said that if the power of x on the numerator is the same as the power of x on the denominator, then the answer to this question as x approaches infinity is the coefficient of both the numerator and the denominator. And clearly here it is -7/14, which is -1/2. Example 2. We want to find the limit as x approaches infinity of 7x raised to the power 5 plus 3 divided by 3x squared plus 5. So again, we are going to consider the end behavior model, which is take your numerator and take the highest power of x together with its coefficient. So that gives us 7x raised to the power 5 divided by, look at the denominator and take the highest power of x on the denominator, which is 3x squared. Now, let's simplify this expression. That gives us the limit as x approaches infinity of 7x cubed divided by 3. And if we substitute, we get 7 times infinity cubed over 3. And this gives us infinity. So clearly, our answer is infinity. So as we said, if the numerator has a higher power of x compared to the denominator, then the answer to this will definitely be infinity. Example 3. I want to find the limit as x approaches infinity of 4x minus 5 divided by 7x plus 1. Solution. So again, we said take the highest power of x on the numerator with its coefficient, which will have 4x, and take the highest power of x on the denominator with its coefficient, which will give us 7x. Now the limit as x approaches infinity, this will end up giving us 4/7, which is the coefficient of the powers of x. Example 4. I want to find the limit as x approaches negative infinity of 5. And the answer to this is +5. In example 5, we want to find the limit as x approaches negative infinity of 3 minus 2x divided by x squared plus 9. So again, we look at the end behavior model, which is consider the highest power of x on the denominator, consider the highest power of x on the numerator, and consider the highest power of x on the denominator. So if we look at our numerator, the highest power of x is negative 2x. And if we look at our denominator, the highest power of x is x squared. So the limit as x approaches negative infinity, this simplifies to negative 2 divided by x. And if we substitute in our negative infinity in place of x, this gives us negative 2 over negative infinity, which gives us 2 over infinity, which is 0. So the answer to this is 0. Why? Because 2 divided by a very huge number, the answer we'll get will be very close to 0. 2 apples divided by all the people in the capital of Canada, Ottawa. Each person will get a very small part of the apple, which is almost close to 0. So these are just some few examples of limit as x approaches infinity. Let's proceed. So we want to look at definition of horizontal asymptotes. The line y equals to b is a horizontal asymptote of the graph of a function f of x if either the limit as x approaches infinity equals to b, or the limit of f of x as x approaches negative infinity is equal to b. For each of the following, find the end behavior model, evaluate the limit, and find any horizontal asymptotes. Very simple. So note the definition of horizontal asymptotes. So if I find the limit as x approaches infinity of a particular function f of x, the answer that I get, y equals to that answer, is my horizontal asymptote. So if I find a limit to this expression and I get b, then y equals to b becomes my horizontal asymptote. Let's take a look at this example. So in this case, we want to find the limit as x approaches infinity of this particular expression. So this gives us, again, we are going to apply the end behavior model, which we are going to consider the numerator and pick the highest value of x on the numerator, which is 2x, and pick the highest value of x on the denominator, which is 3x squared. And we forget about the remaining part of the function. We forget about them. We only focus on the highest power of x. Why are we doing this? Because we are considering x approaching infinity. Then we simplify this expression. This gives us the limit as x approaches infinity of 2 over 3x. And now, if we substitute our infinity, we have 2 times 2 divided by 3 times infinity, which gives us 0. So this tells us that the answer to this is 0. If the answer is 0, then the line y equals to 0 is the horizontal asymptote. Is that okay? So let's proceed to question number B. in this question, we are going to solve the limit as x approaches infinity, and we are going to find the horizontal asymptote. But first of all, let's find the end behavior model. The end behavior model, we said, consider the numerator and take the highest power of x on the numerator and forget about the rest. So in this case, it is 2x squared. And consider the denominator and take the highest power of x on the denominator. In this case, it is x squared. So this gives us the limit as x approaches infinity, 2/1, and this equals to 2. So clearly, the line y equals to 2 is the horizontal asymptote. And this is our end behavior model. Then question C. We want to solve for the end behavior model and find the horizontal asymptote. So again, we solve this expression for the end behavior model. The limit as x approaches negative infinity. Again, the highest power of x on the numerator is x raised to the power 4. And the highest power of x on the denominator is x. So now we can easily simplify. If we simplify, we have the limit as x approaches negative infinity, x cubed over 3. And as we substitute in our negative infinity, this goes to negative infinity. So this tells us that we do not have a horizontal asymptote. Why? Because infinity is not a value that we can assign to y. So we have no horizontal asymptote. So this is how to find horizontal asymptote. The value that you get when you solve the limit as x approaches positive or negative infinity, that answer is your horizontal asymptote. So let's proceed to look at other questions of infinity. And please take note of the order of this growth rate. You need to memorize this. Normally I use an acronym FEPLSC to remember this. So this is factorials, exponentials, polynomial, logarithmic functions, trigonometric functions, and a constant. Now factorial is the highest, followed by exponential function, followed by polynomial functions, followed by logarithmic functions, followed by trigonometric functions, and a constant is the last. So what does this mean? This means that if I'm finding the limit as x approaches infinity of a factorial, x factorial divided by e raised to the power x. This order helps me to identify that factorial is bigger in terms of power compared to the exponential. So if the factorial has a higher power than the exponential, or has a higher growth rate than the exponential function, then it tells me that my factorial function will get to infinity faster than my exponential function. And for that matter, the answer to this will be infinity. Why? Because the factorial function is going to get to infinity faster than the exponential function. So whilst it's at infinity, the exponential function is still at a finite value. And for that matter, the answer to this will be infinity. Example 2. If I have the limit as x approaches infinity of e raised to the power x over 4x factorial. This tells me that, again, my factorial will get to infinity faster than my exponential function. Therefore, the answer to this will be 0. Why? Because the exponential function will be at a finite number, whilst my factorial is at infinity, and a number divided by infinity is 0. 3. If I have the limit as x approaches infinity of x4 plus 2x divided by x squared times e raised to the power x plus 2. I know my exponential function will get to infinity faster than my polynomial function. And for that matter, the answer to this will be 0. So knowing this order helps you answer these questions faster than usual. So let's delve in to solve some examples. So you have to evaluate the following limit. And question number 1, I want to find the limit as x approaches infinity of sine x over x. And again, I'm going to look at my order. Here I have a trigonometric function and a polynomial function. And clearly, I know that my polynomials will get to infinity faster than the trigonometric function. For that matter, because my polynomial is at the denominator, it will be at infinity, whilst my trigonometric function is at a finite value. So that will be a number over infinity, which will give us 0. So without thinking too much, clearly I know that this will go to 0 using this order of growth function. B, we have the limit of e raised to the power x minus 2x as x approaches negative infinity. So here I'm going to use direct substitution. So I'm going to have e raised to the power minus infinity minus 2 times minus infinity. And this will give us 1 over e raised to the power infinity plus 2 times infinity. And this will give us 0 plus 2 times infinity, which will give us infinity. So our answer will be infinity. Question C. So a similar analogy applies to question C. So here I'm going to substitute directly and compare the answers. So clearly, if you look at this, you realize that if you substitute infinity, you are going to have 5 plus 2 raised to the power infinity divided by 2 minus 2 raised to the power infinity. So again, we apply our end behavior model. We take the highest power of x, which here is 2 raised to the power x. And we take the highest power of x on the denominator, which is minus 2x. This will cancel out, and we'll have the limit as x approaches infinity of negative 1, which will be equal to negative 1. So the answer is negative 1. Now let's look at the similar type of question, but you need to approach it carefully. Why? Because in this case, we are dealing with the limit as x approaches negative infinity. So here, if I do my direct substitution, I'm going to have 5 plus 2 raised to the power minus infinity divided by 2 minus 2 raised to the power minus infinity, which will give me 5 plus 0 divided by 2 minus 0. And the answer is 5 over 2. Now, someone will ask, why didn't we do direct substitution here? The reason is, if you do direct substitution here, you're going to end up with infinity over infinity. You're going to get 5 plus infinity, which is infinity, divided by 2 minus infinity, which is still infinity. And that is indeterminate as well. So we have to look for the end behavior model. And this gives us the end behavior model. It cancels out. We have -1. The answer is -1. Now let's look at E. So with E, again, we find the end behavior model. In the end behavior model, notice we have square root above the highest power of x, which is x squared. For that matter, our highest power will be absolute value of x, because when we get rid of the square root, we'll be left with x, divided by the highest power of x on the denominator, which is 4x. And clearly, this will cancel out, so our answer will be 1/4. Now let's look at question number F. So here we are going to find the end behavior model. Again, we'll have here the absolute value of x divided by 4x. And here, when we substitute because we are looking at negative infinity, means you are approaching, as x approaches negative infinity. So our answer will be -1/4. Note the difference. So this brings us to the end of solving limits as x approaches infinity. But let's go ahead and consider vertical asymptotes. Since we looked at horizontal asymptotes, how do we solve for vertical asymptotes? Definition. The line x equals to a is a vertical asymptote of the graph of a function y equals to f of x if either the limit of f of x as x approaches a from the left is equal to plus or minus infinity, or the limit of f of x as x approaches a from the right is equal to plus infinity. So if a is a constant and the answer to that limit gives us positive or negative infinity, then a is a vertical asymptote. A is a vertical asymptote. Another way of looking at it is if you have a rational function. So I'll give you a simple trick to just look at this function and be able to know whether you have a vertical asymptote at this point. It's simple. So I'll talk about that later, very soon. So we have to find the vertical asymptotes of each function. You have to find the limits of the function as x approaches from the left and the right of each asymptote. Then find the value of the limit at each asymptote. So let's go ahead and solve that question. So how do we solve for this particular question? Very simple. So here we want to find if there is a vertical asymptote. So first of all, we need to factorize this expression. So this gives us x plus 1 times x minus 1 divided by 2x minus 4, which I'll even write as x minus 2, and take 2 outside. Factor 2 out. So if you look at this expression, always find the value of x that will make your denominator to be 0. So the value of x that makes the denominator to be 0 is our vertical asymptote. So clearly, if you look at this expression, you realize that the only value of x that will make only the denominator to be 0 is x equals to 2. So when x equals to 2, you realize that the denominator will be 0, meaning this function will be undefined. And at that point, we have a vertical asymptote. So our vertical asymptote is x equals to 2. So now let's find the limit as x approaches 2 from the left and from the right. So if we find the limit as x approaches 2 from the left of this expression of x plus 1 times x minus 1 all over 2 times x minus 2. Now to be able to do this, consider the number line. This is 2, this is 1, this is 3. So if I pick a number here which is the left of 2, it means I'm considering a number like 1.9. Okay, 1.9. And here I'm considering a number like 2.1. So if I consider 1.9, now if I come here, if I substitute 1.9 here, this will be positive. So everything will be positive. If I substitute 1.9 here, this will also be positive. So I have positive, positive. Then, if I look at the denominator, if I substitute 1.9, that gives me negative. So clearly, I have positive, positive, and negative. And what does that tell me? That tells me that my final outcome will be what? Negative. So my final outcome is negative. It tells me that this function, as I approach 2 from the left, is going to go to negative infinity. And now let's find the limit as x approaches 2 from the right of x plus 1 times x minus 1 divided by 2 times x minus 2. So clearly, again, we're going to use the same approach. So I'm going to the number line, and I'm picking a number which is on the right of 2, which is 2.1. If I substitute 2.1 here in place of x, this will give me positive. This will give me positive. Remember, it's 2.1. This will give me positive. So clearly, it tells me this is going to positive infinity. So if this is going to positive infinity, why? Because my final output is positive. I realize that the two are not the same. The left-sided limit and the right-sided limit are different. One is going to positive infinity, the other is going to negative infinity. Therefore, the limit as x approaches 2 from both directions of x plus 1, x minus 1 divided by 2 times x minus 2 will be does not exist. Does not exist. Awesome. So let's proceed to example number B. So example B, the same analysis pertains to example B. First of all, we are going to simplify this expression, which will give us 1 minus x divided by, we factorize our denominator, and we get x minus 3, x minus 1. Now, we are looking for the value of x that will make only the denominator to be 0. So try it and see if you can answer it correctly. Only the denominator to be 0. So the value of x that will make only the denominator to be 0 is x equals to 3 only. And that is our vertical asymptote. Now someone will say, what about x equals to 1? Now if you substitute x equals to 1, you're going to get both the numerator and the denominator to be 0. And that is a different thing. That gives us a whole. So we have a whole at x equals to 1. So the value of x that gives us 0 on the numerator and the denominator is what we call a whole. So there is a whole at x equals to 1. Why? Because both x equals to 1 will give us 0 on both the numerator and the denominator. But x equals to 3 will only give us 0 at only the denominator. So we have a vertical asymptote at x equals to 3. And for that matter, we are going to find the limit as x approaches 3 from both the left and the right. Of 1 minus x divided by x minus 3 and x minus 1. So again, if I consider the number line, I have 2 here, I have 3, I have 4. So I'm picking a number on the left of 3, which will be here. So I'm picking 2.9. So if I substitute 2.9 in place of x, what do I get? I get negative here. If I substitute 2.9 here, I also get negative. If I substitute 2.9 here, I get positive. Now, positive times negative is negative. Negative cancelling the numerator negative will give me positive. So this tells me that this guy is approaching positive infinity. So clearly, this gives me positive infinity. Then, let's find the limit as x approaches 3 from the left, from the right. So 1 minus x divided by x minus 3, x minus 1. So again, I'm going back to my number line, and I'm picking a number which is between 3 and 4. And that could be 3.1. If I substitute 3.1 in place of x, it gives me negative. And if I substitute 3.1 here, I get positive. 3.1 here, I get positive. Negative divided by positive is negative, so this goes to negative infinity. And because the two are not the same, we'll say that the limit as x approaches 3 of 1 minus x, x minus 3 times x minus 1 equals to does not exist. Because the left-sided limit is not equal to the right-sided limit. Now, let's look at the last one. Again, we want to find the value of x that will give us a vertical asymptote. And we said that to find a vertical asymptote, find the value of x that would make only the denominator to be 0. So here you realize that if I substitute x equals to -1, only my denominator will be 0. So it tells you that there is a vertical asymptote at x equals to -1. So now let's find the limit as x approaches -1 from the left of our f of x. And again, if we go back to our number line, we have here -1, -2, we have here 0. So the left of -1, we are considering a number here. So let's consider -1.1. So if we substitute -1.1 here, we are going to get our numerator to be positive, and our denominator will be positive because we are going to square the negative, which will be squared. So here will be positive, so we are going to positive infinity. Then, if we find the limit as x approaches -1 from the right of f of x, so the right of f of x means we are here, we are picking a number -0.9 or -0.01, any of these numbers. If we substitute that here, You realize that 1 is bigger than that number, so this will give us positive. And our numerator is also positive. So for that matter, our answer is positive infinity for that as well. And what does that tell us? That tells us that the limit as x approaches -1 of our f of x is equals to infinity, positive infinity. Why? Because the left-sided limit and the right-sided limit are the same. So this brings us to the end of vertical asymptotes. Let's look at a graph dealing with limit as x approaches infinity. So here we have questions to answer and we have our graph of f of x. So use the graph to evaluate the following limits. The first one, A, says we should find f of 0. So we go to our graph and locate 0. And where do we have it shaded on 0? We have it shaded at -1. So it tells us that f of 0 equals -1. So now let's look at question B. So with question B, it says we should find the limit of f of x as x approaches -infinity. So this is our x-axis, and this is -infinity so far as x is concerned. So as we approach -infinity on the x-axis, our graph will be at what? 2 on the y-axis. -2 on the y-axis. So this gives us -2. The next one says we should find the limit of f of x as x approaches infinity. So this is infinity, positive infinity on the x-axis. So as x approaches positive infinity, our graph gets closer and closer and closer to 0 on the y-axis. So this will be equal to 0. The next one, it says we should find the limit as x approaches 2 from the right. So we go to +2. This is the right of +2. So as we approach 2 from the right, our graph increases unboundedly to positive infinity. So the answer here will be positive infinity. The next one, it says we should find the limit of f of x as x approaches 2 from the left. So as x approaches 2 from the left, this is 2, and this is the left side of 2. So as we approach 2 from the left, our graph decreases unboundedly. So this goes to -infinity. And the last part, it says we should find f of 2. F of 2, we'll go to 2 and find, do we have any shaded value in f of 2? No. So here it is undefined. And this answers the question on the graph involving limits as x approaches infinity. So now let's take a look at the properties of infinite limits. Let C and L be real numbers, and let f and g be functions such that the limit of f of x as x approaches c equals to infinity, and the limit of g of x as x approaches c equals to L. So this is a finite number, this is an infinite number, infinity. So the sum or difference, if you add a number to infinity, you will still get what? Infinity. If you subtract a number from infinity, you still get infinity. So the answer is infinity. Product, if you multiply a number to infinity, you end up with infinity. The same thing, if it is -infinity times a number, the answer will still be -infinity. And now, if you divide a number by infinity, you end up with what? With 0. So a number divided by infinity is 0. So take note of these properties of infinity. The next one brings us to the definition of continuity, continuous at a point. So we are looking at point continuity. We are saying that a function f is continuous at a point C when these three conditions are met. First, f of c must be defined. It must not be an undefined function. It must be a defined function. It must have a definite value. 2, the limit of the function f of x as x approaches c must exist, meaning that the left-sided limit is equal to the right-sided limit. 3, 1 and 2 must be equal. The limit of f of x as x approaches c must be equal to f of c. If these three conditions are satisfied, we say the function is continuous at the point C. And this is the official definition. A function is continuous on an open interval AB when the function is continuous at each point in the interval. A function that is continuous on the entire real number line, that's from negative infinity to infinity, is everywhere continuous. It's not point continuous, it is everywhere continuous. So let's take a look at some graphs to help our understanding. Now, if you look at this graph, you realize that there is a hole in the graph. So this kind of graph is not continuous. So this graph is only continuous from C to B and is continuous from A to C. It is not continuous from A to B. Why? Because there is a hole in the graph. And also, you can clearly see that there is no specific value for f of c. F of c does not exist. F of c is undefined. F of c is undefined. Now, if you look at this second graph, also you realize that even though f of c is defined, there is a jump. And this jump makes the function not to be what? Continuous. So this function is not continuous as a result of the jump. Now, if you look at this graph, you realize that even though f of c is defined, again, there is a hole in our graph. So therefore, this function is not continuous because the limit is not equals to f of c. So the limit exists, all right, but the limit is not equals to f of c. Now, in this case, the limit does not exist because there is a jump. In this case, the limit exists, but it is not equal to f of c. F of c is undefined. These are the conditions for which we say that the graph is not continuous. It's not continuous. Now, there are specific names for each of these. So this is what we call the removable discontinuity. We can find the value of f of c and get rid of this discontinuity. We can fill the hole. And once we fill this hole up, the function becomes continuous. For this, we cannot fill the gap between the two functions. It's too wide. There's a jump, so we cannot fill it up. So we call it non-removable discontinuity. You cannot remove the discontinuity. And also in this case, we call it a removable discontinuity because we can fill up the hole. So please take a note of that. When the limit is not equal to the function, it's a removable discontinuity. When the limit does not exist, it's non-removable discontinuity. And the limit exists, but f of c is not defined, it is also a removable discontinuity.